Unifying quantum and classical computers. Why should we talk about this? Well, for long, physicists has been obsessed with unifying quantum and classical things, like the fundamental theories of nature. But this is a way too hard of a problem for us to solve. So today we're going to talk about unifying quantum and classical computers. And if this is not a good enough motivation for why we should talk about this, then perhaps we should start by asking, why are we all here? I don't mean why quantum mechanics and general relativity conspire to bring us all to existence. I mean, why are we all here today in this room? And I believe that we are all here in this room because we share a single common goal, and that is to reach practical quantum computers. I think that our entire community, each and every one of us believes that this is achievable, that we can get to quantum computers that can solve hard and useful problems. And while the progress in the field has been quite amazing, with more and more qubits on a single quantum processor, and with higher and higher quantum volumes, that's a measure of the quality of the quantum processor, and also with more money that's going into the field, every year we're seeing this almost exponential, more than exponentially growing graph. We also know that that we have quite a long road ahead. And there are many challenging obstacles to reach quantum practicality. So how can we accelerate, how can we drive faster along this road to reach our common goal? Well, one of the more interesting and more important answers that we've been discussing and that actually became clear and clear in recent years in the community is that to reach quantum practicality, we really need to integrate very tightly quantum and classical processing. This is kind of like a turbo engine. I view it almost like the nitros that Van Diesel is using to win every race. Yeah. And this is now there are lots of works and publications about this. So let's break it down a little bit to understand why this is so important. Well, to reach useful applications, we really need to go through many stages. First, when you just start working with a new quantum processor or QPU, you need to calibrate it. That means we need to extract the parameters of the QPU and the parameters of the operations that we perform on the QPU. And that's actually done, the extraction of the parameters is actually done by a classical processor. And in fact, this is one of today's bottlenecks of the field for both performance and uptime. And this could actually be accelerated dramatically if we can close this quantum classical loop faster and perform more frequent and much faster calibrations. Even after we calibrate the quantum processor, we still have the number one most challenging problem we have today with quantum computers, and that's that we still have a lot of errors. So we run something on the quantum computer and we get the wrong answer. So the first way to deal with these errors is to do what we call error mitigation. And that's using classical optimization techniques to sort of design the signals that we send to these QPUs to operate them so that we can sort of avoid the errors. So this is called error mitigation. And again, it requires classical processing. And the ultimate way to deal with the errors is what's called quantum error correction, where we actively correct errors during the runtime of the quantum algorithm by continuously probing the QPU and actually performing heavy classical algorithms on the classical side to decode the errors, to infer what errors occurred on the QPU so that we can fix them as they come. And this is perhaps the most demanding example for why we need this tight quantum classical processing. And even after we build a fault-tolerant large-scale quantum computer and do error correction, and we can solve a practical problem with a quantum computer, this problem is probably going to be a small subtask out of a larger workflow that solves a real-world problem. So the QPU is like an accelerator. It's good for some problems, and again, we will have to integrate it with the entire compute architecture so that we can run efficiently these real-world application workflows. So we need now to combine all of this together and build these unified architectures and to run these quantum classical hybrid workflows efficiently, and also to run them, to program them very productively. And this is really fascinating problem to have. One of the reasons why we started our company, Quantum Machines. So today I want to tell you a little bit about how we see the requirements for what we call quantum classical processing, and what we are doing at Quantum Machines to try to meet some of these requirements. Okay, so the first thing is to really define what we mean by quantum classical processing. And according to our definition, at least, we need to have a full loop. We call it a full quantum classical loop, where we start by doing some quantum processing on the quantum processor, doing some quantum operations. This is happening on the quantum side. Then performing some quantum measurements and sending the data, the qubit measurement data, to the classical processor, performing some classical processing on the classical side, and then generating new quantum operations that depend on this classical processing back to the QPU. Okay, so we need to have this full loop. And perhaps the most important number that we're measuring for this quantum classical processing loop is what we call the classical feedback latency. So this is basically the time that it takes us from the moment we measure the qubits, send the data, do all the classical processing until we generate new quantum operations and actually send it to the QPU, okay? So this is the classical feedback latency, and this is how we define quantum classical processing. Now, we looked into all the various use cases and requirements, and we identified 3 categories for this quantum classical processing. The first one is what we call quantum real-time, or QRT. This is where we need the latency to be much smaller than the coherence time of the QPU. Okay, this happens, for example, in this is a simple example where we want to reset a qubit. We want to bring a qubit to its ground state or to the 0 state. So we measure the qubit, and then if it's 0, we don't do anything. But if it's 1, we need to apply an operation to bring it to the ground state. And of course, we need to operate, we need to measure, then do processing, then make a decision, and then generate new quantum operations. This has to be faster than the time that it takes the qubit to switch states. Otherwise, the measurement doesn't mean anything, the qubit already changed. So we have to do this entire thing much faster than the coherence time of the qubits. Then we have system real time. This is a different requirement for quantum classical processing. So one of the main issues with today's quantum computers is that many of the system's parameters, they keep drifting. So here you see an example where we see the qubit frequency. This is how it drifts with time. There are many reasons for it. If we could probe the qubit frequency every once in a while and fix it, okay, but this requires classical processing, this requires measuring the qubits, understanding what the frequency, how it changed, and then correcting these parameters, we can actually fix that. This is what you see in the blue line there. It's really straight. This is because we applied this quantum classical loop to retune the qubit frequency. And this is actually very dramatic. It could have a dramatic effect, but we have to have this feedback loop being faster than the drifting time, right? If I measure the qubits, I measure the frequency, but then there was another jump, and so I cannot correct it anymore. So this is system real-time quantum classical processing. And the last category, and yes, if we can do that, we can really improve operational fidelities, we can improve stability and robustness of the system, and also utilization. We can have actually higher uptimes because we keep the system calibrated all the time. The last category, which is very important, is near quantum real-time, or simply near real-time quantum classical processing. This is slightly different. Here we just want the latency, the classical latency, to be smaller or comparable with the quantum processing time. This is a bit different than the 2 previous categories. I don't need the classical latency to be smaller than something in order for the protocol to work. Like with the reset of the qubit, that I need to operate faster than the qubit is changing its state, or where I need to operate faster than the drift of the system. Here, it's just because I don't want the classical processing to block or to bottleneck the entire application. Okay, so I want to be limited by the quantum time, by the quantum operation times, the gate times of the QPUs, and so on. So, and then we'll build better QPUs, and then we'll push the classical. So this is the usual game where we want basically to push performance, to push runtimes to be minimal by using tricks like fast communication and parallelization, etc. We actually took all of these requirements, we took all the use cases and categorized them according to these requirements and also other requirements like, so here you see the 3 categories on the y-axis and and another 3 categories on the x-axis. The x-axis here means what kind of feedback do I need to do? Do I just simply want to decide based on the classical processing whether I apply some quantum operation or not, or whether I do real branching, like go to a different subroutine of my quantum program, or whether I want to change parameters of my quantum circuit. So we took all the use cases and categorized them, and also created benchmarks for these quantum classical use cases and categories that you can, I'm encouraging you to see in our archive paper that we recently published. So won't have time to go into all of this, but this is kind of where we are with this. And we're now thinking how we can meet these requirements, right? So I want to tell you a little bit about what we are doing at Quantum Machines to meet some of these requirements. So at Quantum Machines, our mission is to accelerate the realization of practical quantum computers. How is this related to quantum classical integration? It turns out that at the heart of the quantum computer actually has classical hardware and software in it. So we all know about the quantum processor, where we have the qubits and the entanglement and all the quantum magic, but we also need to have another system, a classical system, that communicates with the quantum processor and actually operates it. And this is called the control and orchestration system. It typically communicates with the QPU using fast radio frequency signals. So at Quantum Machines, we're developing the control and orchestration system for quantum computers. We developed a platform that we call the OPX platform that allows to control a variety of quantum processors and devices from many different types of qubits and extract the best performance out of them. At the heart of our technology, we've developed a processor, a new type of processor. This is not a quantum processor, but a classical processor that communicates. This is the classical processor that communicates with the quantum processor and tells it what to do. And for the very first time, we've integrated classical compute engines, very general classical compute engines, into the heart of the quantum control system by integrating them into the pulse processor. So we brought classical compute engines as close to the qubits as possible. Basically, the same chip that orchestrates the quantum operations can also perform classical operations. And you program this pulse processing unit using our pulse level programming language, QA, that allows you basically to write at the lowest level of the quantum computer. This is, you can think about it as like the assembly level language of the quantum computer, to write quantum operations and classical operations in the same code and the interactions between them. Today, we're offering an entire stack of control solutions, going all the way from cryo control equipment, cryo control electronics, through room temperature controllers, and a variety of software infrastructure tools that are necessary to start to integrate to general classical compute and to manage the entire quantum computing stack. We are the largest team in the industry that is focused only on quantum control. We're over 160 people at the company, spread in 7 countries. We also recently merged with the amazing Q2B team from Copenhagen. So we're a single team now with over 200 customers around the world in more than 20 countries. With a comprehensive quantum control suite, as I mentioned. And we are establishing these days also the Israeli Quantum Computing Center. This is a center that's going to provide infrastructure, services, and build a community, a quantum community in Israel. All right, so it's our unique pulse processing technology that's embedded in our control systems that kind of brought classical and quantum integration into its limits, with latencies down to hundreds of nanoseconds. By the way, that's the latency that it takes to respond to the QPU from the control system. But this is not enough. In fact, it's critical now that we integrate with heavier classical processing resources like GPUs and HPC clusters in order to bring the full vision of unified quantum classical machines. And this actually has also stringent requirements. So again, latency is key. We also want to do cost scheduling, so we need to basically schedule the quantum and classical resources together so they don't wait for one another. And we want to co-program the entire thing. So we want a unified software platform where we can program this entire unified machine. So we were exploring how to go about this, and we're doing several things. But about a year ago, we met with the quantum team in NVIDIA, and we're really kind of connected on the same vision of how to connect the GPUs and the HPC resources to the control system. And we shared kind of the same vision and the same wish to create enabling technology around this. So now we're introducing DGX Quantum together. Here we're bringing our control technology together with the best in class, the most powerful accelerated computing platform today, the NVIDIA platform, specifically the Grace Hopper platform, together to create this new kind of quantum classical integration. DGX Quantum is going to basically have an ultra-low latency interface between the quantum controller and the GPU. We write directly to the GPU memory via our interface, targeting microseconds or below microsecond, actually, data transfer times. And this is going to deliver unprecedented performance in this quantum classical processing that I told you about. So the cherry kind of on top of this is that we are going to integrate it all into CUDA and CUDA Quantum. So you can program your hybrid algorithms in CUDA and CUDA Quantum. CUDA Quantum will compile to QA that runs on the OPX and takes advantage of this fast lane between the controller and the GPU. We really think that this, together with our core technology of the pulse processing unit, is going to deliver to quantum computer developers who are our customers and HPC centers that want to integrate these quantum computers into their platforms to allow them to enjoy a performance-defining technology kind of out of the box and to push the field faster than ever. So this is sort of what I wanted to tell you about what we are doing in quantum classical processing, and I'll be happy to take some questions. Thanks.
Yeah, we have time for one question, I think, for Yonatan. Feel free to ask and raise your hand if you're brave enough. Otherwise, you can meet Yonatan anywhere in the networking room or what. Any questions? All right, thank you very much, Yonatan. Oh, one question, all right. Can you speak very loud? It's great.
You're developing the classical processing also. Is that, oh, that was loud. Are you also developing the chips yourself, so the layout and architecture of the chips yourself?
For the pulse processor?
Right.
Yeah, so the pulse processor is an architecture of a chip, but we're actually implementing it on FPGAs today. This is a very good question, because going to the future of the field, yes, these pulse processing units would have to be made in silicon chips, but today we're still working with FPGAs to keep the flexibility of the design. So in principle, we're kind of releasing a new pulse processor every few months. We keep developing the architecture and changing it and modifying it according to how the field is being developed.